Have you ever heard of white holes? They are the opposite of black holes, theoretical structures into which nothing can enter, but from which everything shoots out, and where time flows backwards. What if we told you that these are not just mathematical constructs, but that some scientists believe that the Big Bang was actually a white hole? This could explain not only how the universe began, but also how we were ejected from another universe. Perhaps we are the last cry of a dying universe. Are you ready to dive into this incredible idea that turns the rules of science upside down and changes the direction of time? Because after watching this video, you will never look at the universe the same way again. 1. What is a white hole, and could it really exist? A white hole is theoretically the opposite of a black hole. While a black hole sucks in matter and light, a white hole ejects it outward. The equations of general relativity suggest that when time is reversed, black hole solutions could transform into white holes. However, whether such objects can naturally form in the universe remains a subject of debate. Is a white hole merely a mathematical solution, or could it be an observable structure? The answer to this question is one of the greatest mysteries of the universe. Finding an observable white hole has not been possible to date. This is because white holes are expected to create serious energy and radiation chaos around them as they eject matter. However, astronomers have not yet observed any structure indicating such behavior. This suggests that white holes either do not exist or have not yet been detected correctly. Nevertheless, some gamma-ray bursts and supernovae may provide clues about such possibilities. At the intersection of quantum physics and general relativity, white holes offer intriguing possibilities. Especially in the context of Hawking radiation and the information paradox, white holes can be described as structures that prevent information loss. Some physicists suggest that a black hole could eventually transform into a white hole and expel the information it has absorbed. This implies that black holes might not be infinite, dead ends, but rather portals for recycling. White holes are structures that cause us to question the limits of our physical universe. Despite the lack of definitive proof of their existence, the fact that scientists continue to seriously debate this topic indicates that there is a significant gap in our understanding of the nature of the universe. White holes may be high-energy phenomena that are too short-lived to be directly observed. And perhaps that is precisely why the question of whether the Big Bang itself was a white hole is being seriously considered. By the way, if you like my video and subscribe, that is the most effective way to support me. 2. Where did the idea that the Big Bang could be a white hole come from? This idea was put forward by physicists working on the nature of time and black holes, particularly in cosmology. Starting in the mid-20th century, when the time reversal solutions of black holes were studied, the existence of a theoretical structure, the white hole, inevitably emerged from the equations. However, the question of how and when these objects could have emerged in the universe remained unanswered. At this point, some theorists proposed that the Big Bang itself could have been a white hole on a universal scale. This is because the Big Bang, like a white hole, begins with a sudden outward release of energy and matter from an apparent singularity, a point of infinite density and smallness. This feature aligns closely with the theoretical definition of white holes. Moreover, the cosmic microwave background radiation emitted from the Big Bang may carry traces of this massive energy release. Therefore, some astrophysicists support the idea that the birth of our universe was actually a white hole ejected from the black hole of another universe. Another idea that supports this theory is the unidirectional flow of time. Time flows forward in black holes and backward in white holes. If the Big Bang was a white hole, time within the universe may have begun flowing forward after this reverse exit. This perspective offers a different explanation for the problem of time symmetry in the universe. Why does time only flow forward? Perhaps the Big Bang was the event that determined this direction. In conclusion, this theory is a powerful but speculative assumption that plays with both general relativity and quantum physics. Although it has not yet been supported by observation, the idea that the Big Bang was a white hole shows that scientists are looking for crazy but logical ways to understand the birth of the universe. And perhaps the greatest mystery of the universe is that we were indeed born from another universe. 3. Fundamental differences between black holes and white holes. Black holes are the densest objects in the universe. They create a gravitational well so powerful that even light cannot escape. Their event horizon traps matter and information inside. White holes are the opposite. They are theoretical structures where nothing can enter from the outside, but there is a constant exit from the inside. In this sense, black holes can be described as entrances and white holes as exits. Both are connected to each other through time reversal symmetry in Einstein's general relativity equations. We have a lot of observational evidence for the physical existence of black holes. X-ray emissions, deviations in the orbits of stars, and gravitational waves are among the most prominent pieces of evidence. On the other hand, there has been no direct observation of white holes yet. Their existence is theoretically possible, but how they could form in practice is still a matter of debate. Perhaps they have not been detected yet because they are very short-lived, or they emerged in an earlier phase of the universe, such as during the Big Bang. Another important difference relates to the laws of thermodynamics. In black holes, entropy increases, meaning there is disorder and loss of information. White holes, on the other hand, are thought to play a different thermodynamic role, as they are believed to release entropy. This has led some physicists to view white holes as the universe's reset or reboot mechanism. It can even be said that black holes symbolize death, while white holes symbolize birth. In conclusion, the difference between black and white holes is not only physical, but also philosophical. One may represent the end of the collapsing universe, while the other may represent the beginning of a new universe. If white holes exist in nature, we may be experiencing the universe not from inside a black hole, but as we are being ejected from a white hole. This difference is one of the deepest questions determining the direction of our existence in the universe and the direction of time. 4. Was the beginning of the universe an exit or a continuation of collapse? This question is the most fundamental assumption linking white hole theory directly to the origin of the universe. If the universe is a white hole, its beginning could actually be the end of a black hole in another universe. In other words, what we call beginning is actually part of a much larger cycle. This cycle presents a cosmic structure in which universes are born and collapse, then burst out as other universes. This is called the Big Bounce theory. According to the Big Bounce, our universe was born from a collapse. Perhaps the previous universe collapsed onto itself, and the resulting black hole turned into the white hole that started our universe. In this model, the birth of the universe is a doorway out. That is, it is an energy explosion spreading outward from within the universe, not inward from outside. This implies that time, matter, and space were born simultaneously and outwardly. From this perspective, it is possible to say that the Big Bang was not a birth, but an outward explosion. This model is also related to the total entropy in the universe. If information and energy from a previous universe are reorganized in the new universe, this provides a great deal of consistency from a thermodynamic perspective. This makes it easier to reconcile with observational data, such as the direction of time, the density of matter, and the cosmic microwave background. So this is not only a philosophical, but also a scientifically powerful hypothesis. In conclusion, The beginning of the universe is not a zero point. It may be the continuation of a previous process. Perhaps each universe concentrates its own energy, collapses, and gives birth to a new universe. This perspective may also explain why white holes cannot be observed in the universe. Perhaps every white hole is already the beginning of another universe. This idea of a cyclical cosmos suggests the infinity of both time and existence. 5. How does the law of entropy explain the birth of the universe? The second law of thermodynamics states that in a closed system, entropy, or disorder, increases over time. This law is one of the most fundamental physical principles determining the direction of time. The concept of entropy is crucial for understanding why, after an extraordinarily ordered moment, like the birth of the universe, we are becoming increasingly disordered. If the Big Bang was the moment when the universe had the lowest entropy, then the mechanism behind this event must have been very special and extraordinary. Some physicists argue that this extraordinary order could only have been created by a kind of cosmic reset. If the universe was born from inside a black hole and all entropy was cleansed during this process, the white hole theory could provide an explanation for this order. This is because white holes are described as structures that expel information outward, and in this way, they could provide a low entropy starting point for a new universe. In other words, they could create a beginning where entropy is close to zero. This theory also helps explain why time only moves forward. If the increase in entropy determines the direction of time, then a universe that begins with low entropy must naturally move forward. This explains why the past is orderly and the future is chaotic in the universe. If our universe was born from a white hole, its outward ejection of energy and matter could be the natural beginning of entropy increase. Therefore, the white hole theory is not just a visual or conceptual construct, but is also directly related to the laws of thermodynamics. Questions such as why the universe began so orderly and why time has a direction can find a powerful answer in the white hole model. Scientists' research into the relationship between white holes and entropy is not in vain, because perhaps the symmetrical secret of this energy release lies at the heart of the Big Bang. 6. Could the birth of the universe be a rebound? The Big Bounce theory argues that the universe did not have a beginning, but was born from the collapse of the previous universe. According to this model, the universe does not expand indefinitely. At a certain point, gravitational forces prevail and the universe collapses inward. However, this collapse does not result in complete annihilation, but rather in a massive rebound, the birth of another universe. This bounce theory directly aligns with the concept of white holes, because during the collapse of the previous universe, the massive black hole formed compresses the energy and matter it contains to the point where it erupts. This eruption could be the Big Bang of the new universe. The white hole comes into play at this point. Instead of collapsing into itself and disappearing, matter emerges in another universe. In other words, every black hole explodes as a white hole in another universe. This cyclical structure implies the infinity of time and matter. Another strong point of this theory is that it explains the flatness of the universe. Cosmological observations show that the universe is very smooth on a large scale. This smoothness can only be explained by a regular flow of matter and energy from another universe that existed in the past. If there was another universe before ours, its structure and symmetries could have been transferred to our universe. Thus, the need for a zero-point origin is eliminated. In conclusion, the Big Bounce model interprets the birth of the universe not as a beginning, but as a continuation. This is a powerful perspective, both philosophically and scientifically. When combined with the white hole theory, It opens up a new way of explaining why the universe began the way it did, and why it has the properties it does. And perhaps one day, our universe will collapse and pave the way for the birth of another universe. 7. Did time begin at the same time as the birth of the universe? One of the most striking claims of the Big Bang Theory is that time also began at the moment of the explosion. In other words, time is defined as a dimension that emerged with the explosion. According to this idea, the question, "What was there before the explosion?" is meaningless because time did not yet exist. However, if the Big Bang was a white hole, it may not be that time began after that point, but rather that it continued. In other words, time may have simply changed direction. Einstein's theory of general relativity treats time and space as a whole, space-time. If white holes are defined as structures moving in the opposite direction of time, then the Big Bang could actually be a moment when time changed direction. In this case, time existed before the explosion, but its direction was different. This theoretical perspective fascinates physicists who question not why time began, but why it only moves forward. An intriguing piece of evidence supporting this idea is the symmetry breaks in the universe. Instead of time suddenly emerging, its continuous flow changing direction at a certain point could align with the formation of matter in the universe, the decay of quarks, and the breakdown of quantum field symmetries. In particular, mathematical solutions in quantum cosmology allow for such time transitions. These solutions define the Big Bang not as a beginning, but as a transformation point. If this perspective is correct, time is not something that appeared suddenly. It is a phenomenon that flows in different directions in different phases, as dictated by the nature of the universe. And the Big Bang changed this direction thanks to an event, such as a white hole. Thus, time becomes not only existing, but also a direction-changing phenomenon. This idea allows us to rethink not only the beginning of the universe, but also time itself. 8. What is temporal singularity, and why is it important? Singularity is a point at which the physical laws of the universe break down. This concept frequently arises in black holes and the Big Bang. A temporal singularity represents the moment when the definition and measurement of time become impossible. The moment of the Big Bang is a temporal singularity because density is infinite, volume is zero, and physical laws are invalid. Therefore, understanding what happened at that moment is impossible using today's physical laws. This concept of singularity is also related to the theory of white holes. This is because white holes also have an initial moment when they emit energy outward at infinite density. If the Big Bang was a white hole, then it too would have a temporal singularity. However, in this case, time flows outward rather than inward. Thus, the temporal singularity becomes a threshold that alters the very nature and direction of time itself. Physicists introduce quantum gravity theories at this point, as classical physics is insufficient to explain singularities. Quantum effects may limit these infinities, perhaps revealing that time and space behave in a discontinuous manner, forming a quantum foam structure. At this point, singularity becomes the smallest scale dynamic of the universe. Therefore, temporal singularities are of great importance at both the macroscopic and microscopic levels. Ultimately, temporal singularities define the limits of our understanding of the universe. We do not know what lies there, but we know that everything we know originates from there. If singularities allow for an exit, as in white holes, perhaps the birth of the universe is not merely random, but the result of a much deeper and more planned process. And this process is not the beginning of time, but the moment it is redefined. 9. How does quantum gravity affect the existence of white holes? Quantum gravity is an attempt to unify quantum mechanics and general relativity, and this unification is crucial for understanding the existence of white holes. While classical general relativity can describe white holes on its own, it falls short in explaining how they could form in nature. Quantum gravity aims to fill this gap. In particular, the resolution of singularities and the physicalization of infinities are possible with the help of quantum approaches. Some theories, such as loop quantum gravity, LQ2G, argue that the energy concentrated inside black holes can transform into a white hole at a certain point. This transformation is not a classical destruction, but a kind of restructuring process. According to LQG, since time and space are composed of atomic structures, the center of a black hole does not form a singularity. Instead, a backspacing occurs. This makes the emergence of a white hole possible. Thus, a white hole could be the inevitable end of a black hole. In this context, white holes may be information emissions that appear temporarily in the internal dynamics of the universe. The information that enters a black hole is released after a while due to the effect of quantum gravity, but this process cannot be explained in the classical sense of time. This makes white holes important not only physically, but also in terms of information theory. This is because they reintroduce information that we thought had been lost in the universe. Ultimately, quantum gravity takes white holes out of the realm of speculation and makes them theoretically inevitable. Although these theories have not yet been experimentally verified, they are strong candidates for explaining the nature of the universe. If one of these models is confirmed, white holes could become physical realities rather than just mathematical solutions. This would make the idea of the Big Bang being a white hole much more compelling. 10. Scientific explanations for what came before the Big Bang. For scientists, the concept of before is quite complex because it relates to time itself. If the Big Bang is accepted as the moment when time and space began, it seems illogical that anything could have existed before it. However, some theories challenge this understanding. In particular, quantum cosmology and cyclic universe models argue that a universe or phase before the Big Bang is possible. Approaches like loop quantum cosmology suggest that time operates differently at the Planck scale and that the Big Bang was actually a reverse jump. According to this model, the previous universe collapses into itself, and when density reaches a critical threshold, it jumps and a new universe is born. During this process, time may appear to flow backward. Thus, the question, what came before, may find an answer not in the classical sense, but within a cyclical understanding of time. Another explanation is the principle of timelessness. According to this approach, there was no time before the Big Bang, but energy existed in a potential state. This energy could give rise to a universe through quantum tunneling within vacuum fluctuations. In such a quantum birth, the distinction between before and after becomes meaningless because time itself emerges in this process. This view is particularly consistent with Stephen Hawking and James Hartle's no-boundary model. In conclusion, while science cannot provide a definitive answer to what existed before the Big Bang, it is not entirely silent on the matter. Cyclical models, quantum fluctuations, and the idea that time emerges from nothing offer alternative answers to this question. Perhaps the Big Bang is not just the beginning, but the last breath of another universe, and our perception of time is only a small part of this vast process. 11. The symmetrical nature of the universe and mirror universe theories. The fact that the universe appears to be incredibly symmetrical on a large scale is something that has caught the attention of scientists. The distribution of galaxies, the universality of physical laws, and the order of the cosmic microwave background point to the existence of a powerful symmetry in the universe. This suggests that the universe did not arise by chance, but was born under very specific conditions. This symmetry has led some physicists to propose reverse universe theories. Reverse universe theories propose the existence of another universe that is symmetrical to our universe, but operates in opposite directions. In other words, while time flows forward in our universe, it flows backward in the other universe. While matter exists in our universe, antimatter dominates in the other. This symmetry is not merely an aesthetic idea, but also a principle that provides physical consistency. Based on CPT symmetry, charge, parity, time, it has been shown that such reverse universes are theoretically possible. If the Big Bang was a white hole, it could have created a two-way flow of time. In one direction, our universe is born, while in the other direction, a symmetrical universe with time flowing in the opposite direction forms. This perspective defines the Big Bang not just as the creation of our universe, but as an event that simultaneously created two universes. This dual-sided structure is highly consistent with physical laws tied to energy conservation and symmetry. Although such reverse universes cannot be observed directly, their effects may be detected indirectly. In particular, certain neutrino behaviors, time-related anomalies, and cosmic background anomalies could be traces of these symmetrical structures. If this is true, our universe is not alone. It was born alongside its symmetrical twin. And the white hole theory is the strongest candidate for explaining the mechanism of this dual birth. 12. Cosmic inflation and white hole analogies. Cosmic inflation is the theory that explains how the universe expanded at an incredible speed in a very short time immediately after its birth. This expansion explains why the universe is so smooth and homogeneous. However, this sudden expansion also bears a striking resemblance to the white hole theory. This is because white holes are also structures that eject accumulated energy outward in a very short period of time. During inflation, the universe expands faster than the speed of light. This expansion can be thought of as the ejection of matter from a white hole. If the Big Bang was a white hole, this expansion could have been caused by the transfer of its internal energy to space-time. In this respect, cosmic inflation can be defined as a physical process that follows the dynamics of a white hole. In other words, inflation is the cosmological projection of a white hole's explosion from the inside out. This analogy also explains details such as the beginning and end of cosmic inflation. The stopping of inflation at a certain point is similar to a white hole completing its energy discharge. After this point, the universe enters a normal expansion phase. Thus, the dynamic parallels between the white hole model and cosmic inflation increase the appeal of the theory. This perspective treats the Big Bang not only as energy density, but also as a transition mechanism. In the white hole model, the sudden birth of the universe is not random, but the result of a specific physical structure. Cosmic inflation is one of the first effects of this structure. Therefore, when the white hole and inflation theories are combined, the birth of the universe becomes both more mechanical and more meaningful. 13. What does it mean that the universe has no center? Saying that the universe is expanding creates an image of a center in most people's minds. However, according to modern cosmology, the universe has no center. This is because expansion does not occur like a balloon growing from within, but rather as the expansion of space itself from every point. This shows that the beginning of the universe did not occur at a specific point, but rather began simultaneously everywhere. When linked to the white hole theory, this takes on a rather striking meaning. The concept of a white hole is often visualized as matter erupting from a single point. However, if the Big Bang were a white hole, this eruption would occur simultaneously at every point in three-dimensional space. In other words, every point in the universe is, in a sense, the mouth of a white hole. This idea explains why the universe is centerless and why it appears to expand equally in all directions. The cosmic microwave background radiation also supports this idea. These emissions coming from every direction of the universe indicate that the Big Bang occurred equally in all directions and that every point was equally a starting point. This further strengthens the white hole model, as such a symmetrical expansion is only possible with an evenly distributed energy output. This lack of center carries not only a physical, but also a philosophical message. There is no special point at the center of the universe, and therefore, we are not cosmically privileged. If the Big Bang was a white hole, then every part of the universe was born at the same time and began flowing into time simultaneously. This means that all existence originated from the same source. 14. Why does time only move forward? In our daily lives, we observe that time always moves forward. We can break an egg, but we can never see a broken egg return to its original state on its own. This observation is explained not by physical laws, but by the law of entropy. Entropy is a measure of disorder, and according to the second law of thermodynamics, entropy always increases in the universe. It is this increase that determines the direction of time. However, the source of this direction lies in the conditions at the Big Bang. If the universe was born from a white hole, entropy was very low at the moment of its inception. Thus, the universe emerged from an extraordinarily ordered state, and as time progressed, this order began to break down gradually. The reason time flows only forward may be the low entropy state at the beginning. This is consistent with the white hole theory, as a white hole is a central event that ejects energy and information outward. Some physicists describe this one-way flow of time as a cosmic symmetry breaking. In other words, time was symmetrical at the beginning, but the white hole explosion broke this symmetry. As a result, time began to flow universally only forward. This idea also answers the question of why there are still regular structures, galaxies, star systems in the universe. Because the beginning was orderly. Therefore, the direction of time is not only a result of physical laws, but also of the way the universe was born. If the initial moment was a white hole-style explosion, we understand that this one-way flow is not a physical necessity, but a structural one. And perhaps there are other universes or structures where time flows backward. But the fate of our universe is nothing other than to move forward in the direction of this burst. 15. If black holes swallow information, what do white holes do? Black holes absorb everything that crosses their event horizon and never release it again. This property has led to the information paradox, which has puzzled physicists for decades. According to quantum mechanics, information cannot be destroyed in the universe. However, in black holes, this information seems to vanish. This contradiction brings the theory of white holes into the picture. What if the information swallowed by a black hole is expelled from a white hole? White holes are the opposite of black holes in time. That is, nothing enters them, but they constantly emit matter and energy. If a black hole is a repository of information, a white hole could be the mechanism through which this information is expelled. In this case, information would not have disappeared from the universe, but would simply have emerged in another dimension or another universe with a delay. This idea holds great potential for resolving the information paradox. In some physical models, when a black hole shrinks enough or runs out of energy, it turns into a white hole. During this transformation, the information it has absorbed is released. This information may be in an incomprehensible form, such as energy or radiation. However, in the end, the universe does not lose any information. Thus, both quantum mechanics and the laws of general relativity are preserved. If this model is correct, white holes may exist in other parts of the universe and could be releasing information absorbed in the past. This would make them not just exotic structures, but universal memory points. If the Big Bang was a white hole, perhaps we are not the result of this universe, but of information and energy from another universe. In other words, our existence may be nothing more than traces of the past being regurgitated. 16. Loop quantum gravity and the cyclical nature of the universe. Loop quantum gravity, LQG, is one of the pioneering theories that aims to combine Einstein's theory of general relativity with quantum physics. According to this theory, time and space are atomic in structure. That is, they are discontinuous. This perspective eliminates singularity issues. Unlike classical physics, density cannot reach infinity. Instead, a jump occurs at a certain threshold. This jump signifies the rebirth of the universe and, consequently, its cyclical structure. According to LQG, when a universe collapses inward, this collapse does not result in infinite annihilation, but rather in a rebound. This rebound gives rise to a new universe. During this birth, time changes direction. Perhaps a black hole transforms into a white hole. The cyclical nature of the universe reinforces the idea that the Big Bang is not a beginning, but a transition point. This suggests that the universe exists in an infinite cycle. The most striking aspect of this model is that it explains why the universe is so flat, homogeneous, and isotropic. This is because structures from the previous universe leave traces in the new one. This provides a picture consistent with observations. Additionally, this cyclical structure makes thermodynamics and energy conservation possible. The universe resets entropy to zero at the start of each cycle, but can carry forward accumulated traces without erasing them. Therefore, loop quantum gravity is not merely a mathematical proposal, but offers a profound understanding of the structure, nature, and future of the universe. If the Big Bang was a white hole, this theory's cyclic model would align perfectly. Every universe is the remnant of another universe, and we are within a leap where time has restarted. 17. Could the Big Bang be an escape from a black hole? This idea is a powerful hypothesis that reverses the classic definition of black holes and allows us to see the birth of the universe from a completely different perspective. Black holes are thought to suck in matter and light, including information. However, according to some theories, this swallowed matter does not disappear. It simply reappears elsewhere. If this is true, the Big Bang could be the rebirth of matter from a black hole in another universe in our universe. According to this theory, black holes are not only the end, but also gateways. The energy, information, and matter that enter them eventually reappear in another dimension or another universe as white holes. The Big Bang is the first moment of such a reappearance or escape from a black hole. This approach suggests that there is a kind of bridge between black holes and white holes, and that universes are connected to each other. The idea of inter-universal transition gains even more meaning when combined with multiple universe theories. According to this perspective, the cause of the Big Bang is not a random quantum event, but a physical transfer process. In other words, our universe may be the product of a collapse that occurred in another universe. The death of a star there became the beginning of our universe. Thus, the birth and death of universes are linked in a chain reaction. Every black hole is like the seed of a new universe. If this idea is correct, every black hole in the universe is a potential gateway to birth. And our universe is a cosmos born from another black hole. This approach both strengthens the white hole theory and makes the mechanism of the Big Bang more understandable. The explosion is no longer a beginning, but an escape. And this escape, could be the most mysterious link in the creative cycle of the cosmos. 18. Does cosmic background radiation support the white hole theory? Cosmic microwave background radiation, CMB, is the oldest radiation left over from the birth of the universe and is observed today as a homogeneous distribution throughout the universe. These radiations spread approximately 380,000 years after the Big Bang, when the universe first became transparent. These data indicate that the universe was hot, dense, and uniform at its beginning, just as the white hole theory predicts. According to the white hole theory, the Big Bang was an eruption of matter and energy into the universe. If this is true, there should be a trace of this energy discharge. The CMB is considered to be the remnant of this explosion. Its uniform distribution indicates that it formed simultaneously at every point in the universe, which is very close to the idea that a white hole emits energy equally in all directions. Additionally, some small deviations may correspond to turbulence during the outflow. Furthermore, temperature fluctuations in the CMB may, according to some theorists, be evidence of interactions with other universes or remnants of a previous universe. If the white hole ejected information and matter from another universe, these irregularities could be its echoes. In this case, the CMB is not just a remnant, but also a message carrier, a cosmic signature of the moment of the universe's birth. Therefore, the CMB could support not only the classical Big Bang model, but also the white hole model. Its near-perfect but still flawed structure suggests that the beginning of the universe was a high-energy, directionless, but complex explosion. These data, which largely coincide with the predictions of the white hole theory, play a vital role in our understanding of the process behind the birth of the universe. 19. The first seconds of the universe and the collapse of the laws of physics. The first seconds immediately following the Big Bang were the most critical moments in determining the fate of the universe. During this period, temperatures and energy were so high that the laws of physics as we know them today did not apply. Forces were not yet separated, and particles had not yet formed. Under these conditions, time, space, energy, and matter were intertwined, forming a single, dimensionless, cosmic mixture. These complex moments present a chaos that classical physics cannot explain, but which fits with the understanding of white hole theory. Among the events that occurred in these first seconds were the separation of forces, the cooling of the quark-gluon plasma, and the formation of matter-antimatter asymmetry. However, the details of these events have not yet been fully resolved. This is because we have no direct observations of these periods. We are trying to understand this process using only indirect clues obtained from CMB and particle physics experiments. White hole theory comes into play at this point. If the birth of the universe was a white hole explosion, this high-energy environment is its natural consequence. The energy ejected by the white hole may have formed the primordial cosmic mixture we observe. In this case, the absence of physical laws in the first seconds is actually the transition itself. In other words, the laws did not collapse. They merely paved the way for new laws to emerge. This perspective allows us to view the first seconds of the universe not as chaos, but as a moment of transformation. Perhaps the white hole explosion expelled not only energy, but also laws. In this case, physics is not merely a system operating within the universe. It is an order that emerged alongside the universe. This idea could be revolutionary for both cosmology and philosophy. 20. Does the outside of the universe exist, and are white holes the gateway to it? This question encompasses one of humanity's oldest curiosities. What is outside the universe? Modern physics says that there is no outside of the universe, because space itself exists alongside the universe. However, this explanation does not fully satisfy our imagination. The white hole theory, in particular, offers an unusual approach to this question. Perhaps the outside of our universe is another universe, and white holes are the gateway to it. If white holes are passages to other universes, their mouths may be in our universe, while their roots may be in another dimension. In this case, the outside of the universe is another dimensional structure, or a parallel universe. This idea is also compatible with multiverse theories. Models such as string theory and M theory in particular suggest that our universe floats like a membrane within a higher dimensional multiverse. White holes could be the vehicles for passage between these membranes. In this model, white holes are not just exotic objects in the universe. They are also doors, bridges, and transition points. Through these gateways, it is theoretically possible to reach universes with different physical constants and different initial conditions. If the Big Bang was an explosion originating from such a gateway, then we are already within energy coming from another universe. The outside of the universe could be our past. In conclusion, the outside of the universe is not merely a physical space, but could also be a cosmic origin. White holes carry traces of this outside. Perhaps we are not within the universe. We were born from an outside. And this birth occurred from the cosmic womb of a white hole. This idea leads us to reinterpret the universe both scientifically and existentially. 21. The multiverse hypothesis and the white hole connection. The multiverse hypothesis suggests that our universe is not the only one, and that many universes with different physical rules may exist. This idea is taken seriously by scientists who are particularly interested in quantum mechanics, cosmological constants, and fine-tuning problems. However, the nature of any transition or connection between these universes has always been a subject of debate. This is where the white hole theory comes into play. Could white holes serve as gateways between these universes? According to some theories, a black hole formed in one universe could open as a white hole in another. In this scenario, every black hole would be the starting point of another universe. This mechanism offers a structure that physically connects multiple universes. Universes are not only parallel, but also interconnected. White holes are the observable end of this connection, and the Big Bang itself is the result of such a connection from another universe. This view is supported not only at the cosmological level, but also at the quantum level. Phenomena such as quantum tunneling, vacuum fluctuations, and entropy transfer suggest that information or energy transfer between universes may be possible. White holes could be the starting point for such transfers. In other words, white holes are the concrete manifestation of the principle that what is the end in one universe is the beginning in another. Ultimately, the multiverse hypothesis moves beyond the abstract and finds a physical framework in white hole theory. If the Big Bang was a white hole born from the end of another universe, then we are not just the product of our own universe, but of a much larger cosmos. This idea redefines humanity's place in the universe, turning white holes into not just exotic objects, but channels between universes. 22. Traces of white holes in the cosmic microwave background. The cosmic microwave background, CMB, is the oldest electromagnetic trace left over from the birth of the universe. Since these emissions come equally from all directions, they indicate that the universe is isotropic. However, detailed examinations have revealed small temperature and density fluctuations in the CMB. These fluctuations can be explained not only by quantum fluctuations, but also by the energy output at the moment of birth. And this is precisely where a strong connection to the white hole theory emerges. If the Big Bang was a white hole, the energy it expelled outward could have left traces in the CMB. In particular, the symmetry breaks, hot and cold spots, and polarization deviations observed in certain regions could be remnants of such a sudden, high-energy outburst. Data from NASA's WMAP and ESA's Planck satellites provide important clues in this regard. These anomalies could support the white hole scenario. The white hole eruption may not be a one-way explosion, but rather a chaotic energy release at the quantum level. This could explain the irregularities in the CMB. In particular, some physicists suggest that regions such as the cold spot in the CMB could be traces of other universes. If this is true, white holes may not only be evidence of the beginning of the universe, but also of contact with other cosmoses. Therefore, the CMB is not just light that tells us about the early history of the universe. It may also be a cosmic map of the existence of white holes. If this map is read correctly, the fingerprints left by white holes can be discovered. Cosmology could thus become not just theoretical, but based on direct observation of white holes. 23. Can the information paradox be solved in terms of white holes? One of the biggest problems with black holes is the possibility that information that falls into them cannot be retrieved. This contradicts quantum mechanics, which states that information can never be completely destroyed. Stephen Hawking's information paradox has caused black holes to appear incompatible with quantum laws. However, white holes may offer a different solution to this paradox. If black holes do not store the information they swallow forever, but instead eject it back out through a white hole, the paradox disappears. In this case, information only appears to be lost in one universe, but reappears in another place and time. At this point, the white hole becomes not only an exit for energy, but also for information. Thus, the black hole-white hole pair keeps the universal flow of information constant. This model is also highly compatible with quantum information theory. Some physicists suggest that the contents of a black hole are written on a holographic surface, and that this information can be read again through a white hole. This suggests that black holes are not systems that destroy information, but rather systems that transform it. The white hole is the visible result of this transformation. Information spreads throughout the universe, albeit not in its original form, but in a restructured form. In conclusion, white holes may open the door to solving the information paradox. Black holes may not be places where information is destroyed, but rather temporary focal points where it is reshaped and released. Thus, nothing in the universe is lost, only transformed. And the Big Bang may be the explosion of the greatest transformation of information. 24. Why might time run backwards inside black holes? Although the internal structure of black holes is not yet fully understood, according to the theory of general relativity, time and space behave differently in these areas. For everything that crosses the event horizon, time does not flow forward, but vertically and bent. This situation has led some theorists to believe that time may flow backwards inside black holes. If this is true, the interior of a black hole is oriented toward the past rather than the future. And a white hole is the other end of this reverse flow. The reversal of time is meaningful not only in science fiction, but also in terms of thermodynamics and quantum physics. The reversal of entropy could lead to a low-entropy exit, which aligns with the definition of white holes. In this context, the interior of black holes could be regions where time flows backward, and this time, reversal acts as a tunnel leading to the white hole. The white hole is the time-reversed counterpart of the black hole. This is not a mathematical inversion, but could be a physical reality. As time flows backward, the outward flow of information and matter also becomes possible. Particles falling into a black hole are rearranged to emerge from the white hole in reverse time. This suggests that not only time, but also events in the universe can be reversed. A white hole may be the only place where time flows outward rather than inward. If this idea is correct, the Big Bang is not just the beginning of energy, but also the restart of the direction of time. In other words, the beginning of our universe's time arrow is the end of another structure's time reversal. This perspective forces us to deeply rethink both cosmology and the nature of time. White holes may be the only phenomena in the universe that reset the direction of time. 25. The unknowns within the first Planck time of the universe. Planck time is the smallest unit of time and corresponds to approximately 10 to the negative 43rd seconds. This period is so short that it is used to study the first moments of the birth of the universe. Unfortunately, however, the physical laws that will apply during this time period have not yet been clearly determined. This is because our current theories, quantum mechanics, and general relativity, become incompatible at these scales. This is why the Planck time is one of the dark spots of cosmology. This uncertainty provides an important basis for the white hole theory. This is because the processes that took place during this first 10 to the negative 43rd second time interval are thought to have involved extremely high energy and density. If the Big Bang was actually a white hole, this first time interval would be the most intense moment when it ejected energy outward. This could be the moment when the direction of time was determined and the structural rules of the universe were written. Quantum gravity effects dominated Planck time. Therefore, space-time is not flat and continuous. Instead, it has a bubbly, wavy, and uncertain structure. This structure may align with the nature of a white hole. A white hole could have emerged from this quantum foam, giving birth to the classical physical universe. This birth signifies not only the creation of energy, but also the construction of space-time itself. Therefore, Planck time is not merely a physical measure, but also an ontological boundary. Stephen Hawking's information paradox has caused black holes to appear incompatible with quantum laws. However, white holes may offer a different solution to this paradox. If black holes do not store the information they swallow forever, but instead eject it back out through a white hole, the paradox disappears. In this case, information only appears to be lost in one universe, but reappears in another place and time. At this point, the white hole becomes not only an exit for energy, but also for information. Thus, the black hole-white hole pair keeps the universal flow of information constant. This model is also highly compatible with quantum information theory. Some physicists suggest that the contents of a black hole are written on a holographic surface, and that this information can be read again through a white hole. This suggests that black holes are not systems that destroy information, but rather systems that transform it. The white hole is the visible result of this transformation. Information spreads throughout the universe, albeit not in its original form, but in a restructured form. In conclusion, white holes may open the door to solving the information paradox. Black holes may not be places where information is destroyed, but rather temporary focal points where it is reshaped and released. Thus, nothing in the universe is lost, only transformed. And the Big Bang may be the explosion of the greatest transformation of information. 24. Why might time run backwards inside black holes? Although the internal structure of black holes is not yet fully understood, according to the theory of general relativity, time and space behave differently in these areas. For everything that crosses the event horizon, time does not flow forward, but vertically and bent. This situation has led some theorists to believe that time may flow backwards inside black holes. If this is true, the interior of a black hole is oriented toward the past rather than the future. And a white hole is the other end of this reverse flow. The reversal of time is meaningful not only in science fiction, but also in terms of thermodynamics and quantum physics. The reversal of entropy could lead to a low entropy exit, which aligns with the definition of white holes. In this context, the interior of black holes could be regions where time flows backward, and this time, reversal acts as a tunnel leading to the white hole. The white hole is the time-reversed counterpart of the black hole. This is not a mathematical inversion, but could be a physical reality. As time flows backward, the outward flow of information and matter also becomes possible. Particles falling into a black hole are rearranged to emerge from the white hole in reverse time. This suggests that not only time, but also events in the universe can be reversed. A white hole may be the only place where time flows outward rather than inward. If this idea is correct, the Big Bang is not just the beginning of energy, but also the restart of the direction of time. In other words, the beginning of our universe's time arrow is the end of another structure's time reversal. This perspective forces us to deeply rethink both cosmology and the nature of time. White holes may be the only phenomena in the universe that reset the direction of time. 25. The unknowns within the first Planck time of the universe. Planck time is the smallest unit of time and corresponds to approximately 10 to the negative 43rd seconds. This period is so short that it is used to study the first moments of the birth of the universe. Unfortunately, however, the physical laws that will apply during this time period have not yet been clearly determined. This is because our current theories, quantum mechanics, and general relativity, become incompatible at these scales. This is why the Planck time is one of the dark spots of cosmology. This uncertainty provides an important basis for the white hole theory. This is because the processes that took place during this first 10 to the negative 43rd second time interval are thought to have involved extremely high energy and density. If the Big Bang was actually a white hole, this first time interval would be the most intense moment when it ejected energy outward. This could be the moment when the direction of time was determined and the structural rules of the universe were written. Quantum gravity effects dominate at Planck time. Therefore, space-time is not flat and continuous. Instead, it has a bubbly, wavy, and uncertain structure. This structure may align with the nature of a white hole. A white hole could have emerged from this quantum foam, giving birth to the classical physical universe. This birth signifies not only the creation of energy, but also the construction of space-time itself. Therefore, Planck time is not merely a physical measure, but also an ontological boundary. The veil behind the known universe lies within that moment. If a white hole explosion lies behind that veil, Planck time is the cosmic dawn, where the birth pangs of the universe are experienced. And this dawn is still an unobservable but intuitively felt starting line. 26. The physical meaning of traveling backward in time. Although traveling backward in time is a common theme in science fiction, it is a highly complex and still controversial issue in modern physics. The theory of general relativity allows for time loops under certain special solutions. However, these solutions are dependent on very specific conditions and are incompatible with the current structure of our universe. Nevertheless, in some physical systems, it may be possible for time to run in reverse. This sheds light on the nature of white holes. From a thermodynamic perspective, the forward flow of time is related to the increase in entropy. However, in a scenario where entropy decreases, it may be possible for time to run in reverse. White holes can be thought of as representative of this type of situation. In black holes, entropy increases. In white holes, however, energy and information are released, so entropy may decrease. This implies that special regions where time changes direction may exist. At the quantum level, some events are known to be symmetric with time. Therefore, it may be theoretically impossible to distinguish whether an event occurs in the future or the past. However, this symmetry breaks down at the macroscopic scale. If white holes are the macroscopic manifestation of quantum time symmetry, then time flowing backward is not merely a fantasy but physically possible under specific conditions. A white hole could be one of the rare portals in the universe where time flows backward. From this perspective, the Big Bang itself is the moment when time changed direction. That is, time flows forward in our universe because that explosion determined the direction of time. Perhaps in other universes, white hole-like events produce structures where time flows backward. This would indicate that time is not a universal constant, but a directional phenomenon dependent on the beginning. 27. Could white holes be related to dark matter? Dark matter, which makes up approximately 85% of the total matter in the universe, has not yet been directly observed. This matter neither emits nor absorbs light, but its existence has been indirectly detected through its gravitational effects. The question of what dark matter is remains a major mystery in science. Some theorists believe that white holes may be part of this mystery. Most of the energy and particles ejected by white holes were released into the universe at the moment of its birth. Some of these particles may have formed the invisible matter we call dark matter. This is because such particles may have a structure that interacts with gravity, but not with electromagnetic forces. In this case, dark matter is the cosmic legacy of white holes. Additionally, white holes themselves may behave like dark matter. If white holes are extremely short-lived, but formed in large numbers throughout the universe, their effects may still be felt today. These white hole remnants could form the invisible mass around galaxies, influencing their rotational speeds. Such models could also be used to explain the homogeneous distribution of dark matter. Although this theory has not yet been confirmed, a connection between white holes and dark matter would contribute to a better understanding of both the birth of the universe and its current structure. Perhaps the two most mysterious structures in the universe, white holes and dark matter, are different aspects of the same phenomenon. The physical traces of invisible energy, fluctuations, and their infinite echoes. The birth of the universe, according to string theory. String theory argues that all particles and forces in the universe are different modes of tiny vibrating strings. This theory has the potential to unify both quantum mechanics and general relativity. String theory redefines not only particles, but also space-time and the birth of the universe. In this context, it offers unique approaches that could align with the idea that the Big Bang was a white hole. In string theory, our universe exists within a higher dimensional brain. The collision or merger of this brain with another brain could result in the Big Bang. This collision causes a massive energy release in the style of a white hole. This perspective suggests that the Big Bang did not occur only in our universe, but in a multi-dimensional environment. And the white hole is the transition window formed as a result of this collision. One of the interesting aspects of string theory is that time and space emerge as vibrations of strings. This allows us to view the beginning of time not as a fixed point, but as a process. If the white hole is the dynamic that initiates the space-time oscillation of this process, then the birth of the universe is not an explosion, but the result of a transition, a dimensional change. This positions the Big Bang as a softer and more controlled event. According to string theory, white holes are not merely points that disperse the energy of the universe's birth, but rather points of resonance that organize it. The Big Bang is the cosmic echo of such a resonance, and we are on a wave left behind by this vibration in the infinite universe. This approach is one of the most compelling narratives that brings together the physical and geometric nature of the universe. 29. Could white holes preserve information in the universe? In physics, information defines not only what an object is, but also how it was formed and what processes it went through. According to the rules of quantum mechanics, no information in the universe can be completely lost. However, black holes pose a major problem in this regard. If the information that falls into them cannot be retrieved, this would violate the quantum principle. This is where the white hole theory comes into play, because they are seen as structures where the swallowed information can be released back into the universe. White holes are the time-reversed solutions of black holes. In other words, they are regions where nothing can enter but matter and energy continuously escape from within. If black holes swallow information, white holes may release it back into the universe. This process may not occur over time, but the information may be transported in a quantum structure and revealed at some point in the future. This means that information conservation in the universe is ensured through white holes. Some physicists suggest that information is recorded holographically on the surface of black holes, and that a mechanism is needed to re-emit this information into the universe. A white hole could be the active phase of this mechanism. A white hole encodes the accumulated data inside and ejects it outward in the form of radiation, particles, or energy. This emission, though it may appear chaotic in a classical sense, could actually be systematic and carry information. In this case, white holes are not merely physical phenomena, but become the centers of universal memory. The universe can preserve information about its own past through these structures. And if the Big Bang was a white hole, it means that all the cosmic processes we are currently experiencing actually carry information about events that occurred in a past universe. Perhaps we are not stardust, but information dust. 30. Could consciousness be the cause of the birth of the universe? Science tries to understand the birth of the universe by assuming that it is a material structure. However, some physicists and philosophers suggest that the real driving force behind the universe could be consciousness. Although this idea may initially seem metaphysical, it gains deeper meaning when quantum physics and the observer effect are taken into account. If a watching structure is necessary for the universe, then consciousness may have played a structural role in the universe's existence. When this idea is combined with the white hole theory, interesting results emerge. If the Big Bang was a white hole, and that white hole is transferring information and energy from another universe, this transfer could have been done in a conscious manner. In other words, the universe may not have formed randomly. It may have been the result of a conscious choice. This view also explains the universe's tendency to produce mathematically meaningful structures. Some theorists argue that the universe observes itself and is inclined to create conscious structures. The emergence of conscious life is also part of this cycle. If a white hole is a transmission of information and order, the potential for consciousness to evolve within that order may also have been carried over. In other words, the universe experienced a birth that was not only physical, but also mentally potential. Ultimately, explaining the birth of the universe solely in terms of energy and matter may not be sufficient. Perhaps the universe itself is the materialization of a thought. And the Big Bang is not just an explosion, but a reflection of awareness, of consciousness. The white hole is the observable form of this reflection. It is the first thought of the universe. 31. The formation of the first elements of the universe and the white hole. After the Big Bang, the universe was like a sea of plasma. Protons, neutrons, and electrons were freely moving and colliding in an environment of high temperature and density. Within the first few minutes, these free particles combined to form light elements such as hydrogen, helium, and a small amount of lithium. This process is called Big Bang nucleosynthesis. The ratio of these elements helps us understand the conditions of the universe's birth and how the process worked. The white hole model plays a significant role in providing the conditions for this process. If the Big Bang was actually a white hole explosion, the energy and particles released outward would have created the exact environment needed for nucleosynthesis. The protons, neutrons, and energy erupting from the white hole begin to cool as the universe expands, setting the stage for the reactions that will form the first elements. Observations indicate that the universe contains approximately 75% hydrogen and 25% helium, a ratio that largely aligns with theoretical models. This suggests that the universe's origin was not random, but occurred within specific physical laws. The white hole theory may have created the environment necessary for these laws to be applied. In other words, the particles emitted by the explosion are not merely entities, but also possess the potential to construct structures. Therefore, white holes may have served not only as ejectors of matter, but also as regulators that formed elements. To better understand the constructive and organizing nature of the Big Bang, it is necessary to consider the white hole model. This is because this model is a powerful key to explaining that the universe was born not only from chaos, but also from highly sensitive orders. 32. The role of dark matter in the birth of the universe. Dark matter explains why stars do not disperse despite their distance from the center of the galaxy, and why galaxies rotate faster than expected. However, what this matter is, how it formed, and what role it played in the birth of the universe remains unclear. The Big Bang model predicts the existence of dark matter, but cannot clearly identify its source. This gap presents an area where the white hole theory could come into play. The high-energy particles emitted during a white hole explosion could be exotic particles that do not transform into known matter, but have a gravitational effect. These particles may have spread throughout the universe in its early moments, but remain undetectable because they do not interact electromagnetically. Therefore, dark matter can be thought of as the shadow of a white hole. We trace its presence not physically, but through gravitational effects. According to some theories, dark matter is actually composed of particles that travel between universes. If a white hole transfers particles from another universe, these particles could exist in our universe without interacting. This idea explains why dark matter does not interact with light, but still has a gravitational effect. A white hole could have become the birth canal for these particles. In conclusion, dark matter is not merely an unobservable structure, but a cosmic residue accompanying the birth of the universe. When combined with the white hole theory, this matter emerges as the structural skeleton of the universe. This matter we cannot see, but can feel, may be our first visitor from another universe. 33. If black holes swallow information, what do white holes do? Black holes are known as celestial objects that store everything that enters them forever after it crosses the event horizon. This situation creates a contradiction with quantum mechanics, as according to this theory, no information in the universe is ever completely lost. However, no matter what falls into a black hole, no observer from the outside can access this information again. This contradiction is known as the information paradox, and is one of the greatest problems in modern physics. According to some theories, the information believed to be lost in black holes does not actually disappear, but merely transforms into another form. This is where white holes come into play. Because white holes are the opposite of black holes in time. They are structures that release matter and information outward. If a black hole is a door that swallows information, a white hole is the opposite door through which that information erupts outward. These two structures could form a pair that completes the principle of information conservation in the universe. A white hole could be a channel through which not only energy, but also structures carrying meaning are emitted. While black holes hold the information that falls into them, a white hole in another part of the universe could transmit this information outward in the form of energy and matter. This implies that the flow of information in the universe progresses in a continuous and uninterrupted cycle. We might be talking about a cosmic flow, where information does not disappear, but merely changes direction. If the Big Bang was a white hole, this means that our universe is the result of a past that has been lost in another universe. We are the transformed form of information accumulated in an old universe. In this case, white holes are not merely physical explosions. They are universal memory mechanisms that transmit information from the past to the future. The birth of the universe could be a burst of meaning. 34. Is the universe running an algorithm? The fact that the universe operates according to certain rules and laws has led some scientists to believe that it works like a kind of algorithm. According to this view, the universe is not just a physical structure, it is also a functioning system, a kind of cosmic software. This idea is intensely debated, particularly in the fields of information theory, the mathematical universe hypothesis, and digital physics. Every movement of the universe can be thought of as a line of code. When combined with the concept of white holes, this idea of an algorithmic structure yields some fascinating results. White holes could be the 0 points where this universal code is executed. If black holes are the data input areas of this code, then white holes are where the output is produced, where information is rewritten. The Big Bang could be the execution of a line of this algorithm. Let the universe begin. Some theorists explain why the physical constants in the universe are so precisely tuned using this algorithmic model. If the code were written incorrectly even once, atoms would not form, stars would not shine, and life would not emerge. The white hole theory could be the loading point for this code. So the universe's program was started in a white hole, and we are inside this code. Every physical law could be a function, every galaxy a module. In this case, the algorithmic structure of the universe is not only philosophical, but also physical. The white hole is the first line of this algorithm being executed. The Big Bang is not just a physical event, but the moment when a calculation began. And we are subprograms within this great system that are becoming aware of themselves and of the algorithm. Perhaps the essence of the universe is not information, but function. 35. What does the decentralized nature of the universe mean? The expansion of the universe leads us to imagine it as a structure growing outward from a center. However, the absence of a center in the universe is a fundamental assumption in modern cosmology. Expansion occurs equally from all points, like the surface of a balloon. This shows that no point in the universe is privileged, and that every place is equally close to the starting point. The white hole theory fits perfectly with this structure. If the Big Bang was a white hole, then every point in the universe was part of this exit. In other words, a white hole is not just an explosion from a point, but an explosion of existence that occurs simultaneously from every point. This makes the centerless structure of the universe logical. This is because the energy that burst outwards did not come from a single point, but from space-time itself. This also explains why cosmological principles apply in the universe. The fact that the same laws of physics apply everywhere in the universe is the result of the symmetrical explosion at the beginning. If the universe was born from a white hole, this equality was already encoded at the moment of its birth. There is no center because every place is the first moment. This explains the egalitarian, directionless, yet meaningful structure of the universe. In conclusion, the centerlessness of the universe is not a sign of its randomness, but of its deep structural plan. The white hole theory allows us to better understand this plan. We are not outside the universe, but beings born at the same time in every part of it. And there is no center to this birth because everything began at once, everywhere. By the way, if you like my video and subscribe, That's the most effective way to support me. 36. Could the universe be a simulation? The simulation hypothesis has been the subject of serious scientific debate in recent years, not just science fiction. According to this idea, the universe we live in could be a kind of computer simulation. Some physicists believe that the mathematical structures, physical constants, and observable patterns in the universe could support this idea. The white hole theory could play a particularly striking role in this context. White holes could be the trigger mechanisms for this simulation. Just like the moment a game is first started, a white hole loads the first lines of the universe. If the Big Bang was a white hole, then that was the beginning of our simulation. At that point, matter, energy, time, and space were released as programmed. After the simulation began, everything developed according to these initial conditions. An interesting observation that supports the simulation hypothesis is that there is a certain pixelation or resolution limit in the universe. Planck length and Planck time show that the universe cannot be divided into smaller units. This is similar to the resolution limit of a digital world. If the white hole is the starting point of this resolution, then the hardware limit, where our simulation was born, could be right there. In this case, the birth of the universe is not merely physical. It is the result of conscious coding. A white hole is not just a physical explosion, but the triggering of a process. If the simulation idea is correct, we are living inside a code, and the white hole is the first line of that code. Perhaps someone outside of us pressed the start button, and we became the universe. 37. The cosmic censorship hypothesis and white holes. The cosmic censorship hypothesis is an important principle proposed in general relativity. According to this hypothesis, all singularities in the universe, that is, points where the laws of physics break down, must be unobservable from the outside. In other words, the universe does not allow naked singularities. Such structures are either hidden by the event horizons of black holes or are contrary to the nature of the universe. However, the white hole theory directly challenges this assumption. This is because white holes are an obvious form of singularity where time runs backwards. If a white hole exists freely in the universe, then this singularity must be observable by everyone. Since a white hole expels energy and information outward, it is not hidden by an event horizon. Instead, it creates an outward-facing dynamic. This situation may contradict the cosmic censorship assumption, or, more interestingly, white holes could be an exception to cosmic censorship, a type of singularity that only appears at the beginning of the universe and under very specific conditions. Some physicists resolve this contradiction by defining white holes as temporary structures. According to them, white holes only exist for a very short time, and then either disappear or turn into black holes. This makes them almost impossible to observe. However, if the Big Bang itself was a white hole, then this assumption becomes invalid for the entire universe, because the entire universe originated from an observable singularity. In this case, the cosmic censorship hypothesis may be valid for structures outside the universe, but not for the special singularity at the moment of its birth. The white hole may be the only moment when the universe's greatest secret is revealed, an infinity that opens outward, not inward. And perhaps that is why the beginning of the universe is an exception to all the physical principles we know. 38. Reverse flow universe model. The reverse flow universe model defends the existence of a universe in which time flows in the opposite direction of our perception. This model is constructed based on scenarios in which entropy decreases. While the increase in entropy determines the direction of time, its decrease creates a reverse time flow. If such a universe exists, the past in that universe is our future, and the future is our past. When combined with white hole theory, this model becomes even more profound. When white holes are thought of as structures representing the reverse flow of time, they can become the gateway to a universe with reverse time flow. If the Big Bang was a white hole, there could be another universe on the other side, where time flows in the opposite direction. This means that every white hole is a two-way gateway between universes. While time flows forward on one side, it flows backward on the other. Such a model also yields interesting results in a physical sense, because in a universe where time flows backward, life, evolution, and structure could function entirely differently. However, the laws of physics could remain the same. In other words, the reverse flow is not a breakdown of the laws, but merely a change in direction. This suggests that the fundamental structure of the universe is actually time-symmetric, but can flow in different directions due to breaks. If such a universe exists, the point of contact with it could be a white hole. Our universe's origin might have emerged from another universe with reverse flow. And perhaps we are living within a time duality without realizing it. The balance between two universes, one flowing forward and the other backward. The white hole is the central point between these two arrows. 39. What does particle physics say about white hole theory? Particle physics studies the smallest building blocks of the universe and how they interact. The standard model developed in this field successfully explains most of the fundamental forces and particles we know. However, this model falls short when it comes to cosmological issues, such as gravity and singularities. This is where extreme structures like white holes come into play. These structures challenge the limits of particle physics and raise the need for new physics. The white hole theory is particularly discussed at the level of understanding high-energy particles and quantum tunneling. If particles emerging from a white hole can be detected, this could lead to the discovery of new particles beyond the standard model. For this reason, some physicists believe that white holes can form exotic types of matter or dark particles. These particles may originate from white holes, even though they are rare or non-interactive in our universe. At the point where particle physics meets quantum field theories, the energy distribution of white holes becomes quite critical. The spectrum of radiation emitted during a white hole explosion may contain traces of new particle types. For this reason, some cosmologists have begun to interpret gamma-ray bursts as traces of white holes. Each new signal could open a window into the physical conditions of the universe at the moment of its birth. From this perspective, particle physics may possess the tools to either confirm or refute white hole theory. Sufficiently sensitive detectors could capture the information-rich particles ejected by a white hole. And perhaps these particles will reveal that our universe is not merely composed of matter, but of a structure imbued with meaning. 40. Anti-universe theory and the white hole connection. Anti-universe theory posits the existence of another universe that is symmetrical to our own, but has opposite properties. In this universe, antimatter dominates, time flows backward, and the laws of physics are reversed. Theoretically, such a structure is based on CPT, charge, parity, time, symmetry, which is one of the cornerstones of modern physics. If such symmetry exists in the universe, white holes may carry the physical traces of this transition. White holes, as structures where time flows backward, could represent the moment of the anti-universe's birth. In other words, during the Big Bang, not only our universe, but also its exact opposite, an anti-universe, may have been born. If there is matter in our universe, antimatter dominates on the other side. If time flows forward here, it flows backward there. A white hole is the first moment when these two universes separated. This kind of dual birth model provides meaningful answers to some physical questions. For example, why is there so little antimatter in the universe? Because antimatter is concentrated on the other side. It also explains why time flows in one direction, because time is symmetrical in the total system, but each universe has chosen a direction. This suggests that a white hole could be a cosmic portal opening to both sides. If this is true, we are not alone. At the same time as us, another universe was born, operating under the same physical equations, but with opposite conditions. The white hole was the center of this birth, and perhaps one day, the echoes of these two universes will manifest themselves in the cosmic background or in the behavior of particles. Then we will understand that the universe hasn't one, but a dual existence. 41. Will the expansion of the universe stop or collapse? The fact that the universe is expanding was discovered in the early 20th century through the observations of Edwin Hubble. As galaxies were seen moving away from each other, it was accepted that the universe was not static, but dynamic. However, how long this expansion will last, and what forces are influencing it, remain unanswered questions. According to some scenarios, the universe will expand forever, while others suggest that expansion will eventually stop, and collapse will begin. The white hole theory offers a different perspective on this question. If the universe originated from a white hole, the energy that erupted outward at the beginning triggered the expansion. However, if this energy is limited, it may lose its effect at some point. In this case, the gravitational pull of the universe would become dominant, causing expansion to slow down, stop, and then reverse. This reversal would mean a new collapse process, and perhaps a new Big Bang with another white hole. On the other hand, the repulsive force we call dark energy seems to be accelerating the expansion of the universe. This supports the Big Freeze or heat death scenario, in which the universe expands infinitely. When combined with the white hole model, this scenario depicts an end in which time and energy become increasingly thin and slowly disappear throughout space-time. However, if the white hole only released energy outward for a certain amount of time, this repulsive force must also be finite. Ultimately, the fate of the universe may depend on the nature and energy of the white hole from which it was born. Will expansion stop, or will it continue forever? The answers to these questions may be shaped not only by gravity, but also by the initial conditions at the universe's birth, the character of the white hole itself. Perhaps the universe will not end in infinite expansion, but will reset itself with another collapse and continue the cycle. 42. Was the beginning of time really a moment? The question of whether time has a beginning is one of the common dilemmas of physics and philosophy. The classic Big Bang model states that time began with space. In other words, there was nothing before it. However, this explanation is intuitively unsatisfying. If time was born in an instant, what was the nature of that instant? Since even the concept of an instant contains the idea of time, this idea contains an internal contradiction. The white hole theory revisits this problem. If the Big Bang was a white hole, then the beginning of time may not have occurred in an instant, but rather through a transition. In this case, time is not an entity that suddenly exists. It could be a flow derived from another process. A white hole may not be the place where time emerges from nothing, but rather a threshold where it changes direction. This positions the concept of beginning within a continuum. This transition model finds particular resonance in quantum cosmology. It is argued that time is not a classical line, but a structure governed by probabilities, emerging through quantum transitions or fluctuations. In this model, the beginning of time is not an event that explodes in an instant, but a pattern emerging from uncertainty. A white hole could be the physical trace of this pattern becoming visible. In conclusion, time may not have begun at a specific moment. It could be a new direction, a new order, emerging from another state of existence. The white hole is the trigger for this new order. Thus, time is not born, it is transformed, and we are the conscious witnesses of this transformation. 43. What is time symmetry breaking? Most physical laws are symmetrical with respect to time. It does not matter whether an event occurs forward or backward in time. The equations still work. However, in the real universe, time symmetry seems to be broken. An egg can be broken, but we never see a broken egg spontaneously reassemble itself. The reason for this asymmetry is entropy and the second law of thermodynamics. However, this explanation does not fully account for why time is one way. The white hole theory offers a new perspective on the breaking of time symmetry. This is because a white hole represents a region where time flows backward, while a black hole is a structure that collapses within time symmetry. A white hole is its opposite, a structure that expands outward in time. If the Big Bang was a white hole, then time symmetry may have been broken precisely at that point. This break could be the first split that initiated the one-way flow of all events in the universe. According to some theories, time symmetry has only been broken in our universe. It may still hold in other universes or other time frames. This suggests that white holes are not just transitions that alter the flow of time, but also enable the diversification of time structures. If there are universes where time flows in different directions, this symmetry break must be considered within a broader framework. From this perspective, the breaking of time symmetry is a consequence of the fundamental nature of the universe. We are beings living within this break. The white hole is the phenomenon that makes this break possible or initiates it. The direction of time is determined by the direction from which we emerged. Perhaps there was an alternative to time, but we chose this path. 44. Could the Big Bang be the result of a symmetry breaking? To view the birth of the universe as merely an explosion may mean ignoring the order and structural transformation behind it. Physically, the Big Bang was not just an emission of energy, it was also a transition during which symmetry breakings occurred. In the beginning, all of nature's forces, electromagnetism, weak and strong nuclear forces, gravity, were united into a single force. This symmetrical state broke down as the universe cooled. During these symmetry breaks, particles gained mass, forces separated, and the foundations of subatomic structures were laid. If the Big Bang was a white hole, this symmetry breaking could have been triggered by its physical effects. The energy emitted by the white hole not only created chaos that built new structures in the universe, but also enabled distinctions between these structures to form. We transitioned from a state where everything was one to a moment when diversity was born. The symmetry breaking may have occurred not only in the physical realm, but also in temporal and spatial dimensions. Initially, there were no concepts of direction, time, or place. Everything was one and the same. However, the white hole shattered this unity. This fragmentation was the primordial crisis that gave rise to the universe's ordered structure. Every structure and every particle in the universe is an echo of this breaking. Every force separation is a trace of the birth pangs of the universe. Thus, we should see the Big Bang not only as a violent release of energy, but also as a major structural rupture. The white hole may have given birth not only to energy, but also to new physical rules. And today, we live in a universe shaped by these rules. Symmetry breaking is the creative crack that fills the universe with meaning. 45. Why have white holes not been observed to date? White holes are cosmic structures that are theoretically possible, but have not yet been observed. This leads many people to ask, why haven't we seen them? Indeed, while the existence of black holes has been almost confirmed by indirect observations, white holes have not yet been physically verified. Does this absence mean that they are not real, or do they hide a deeper cosmic mystery? One possibility is that white holes only appeared at the moment of the universe's birth, i.e., during the Big Bang. If the entire universe is a white hole, this event occurred only once, and on a scale that formed the entire structure of the universe. This explains why white holes cannot be observed, because there was only one, and that was the universe itself. In this case, expecting another white hole would mean waiting for the birth of another universe. Another possibility is that white holes have extremely short lifespans. Perhaps they explode outward with incredible energy upon formation and immediately cease to exist. This brief lifespan could make detecting them nearly impossible. Additionally, the nature of white holes may cause them to emit radiation that is not detectable within the electromagnetic spectrum, rendering them invisible. Our inability to recognize the signals they emit may also be the reason for their silence. Ultimately, the fact that white holes cannot be observed may not indicate their absence, but rather the limitations of our technology and understanding. Perhaps they have already been observed but not recognized. Perhaps a gamma ray burst or a signal recorded as an anomaly was actually the echo of a white hole. And when we realize it, we will hold the key to the great mystery of how the universe began. 46. Why the universe is so homogeneous. When we look at the large-scale structure of the universe, a striking fact emerges. Galaxies, galaxy clusters, and voids are distributed throughout the universe with almost perfect homogeneity. This raises a problem known as the flatness problem in the Big Bang model. If the universe was born from a random explosion, why is everything so equal and orderly? The answer may lie within the white hole theory. White holes, which are structures that direct energy and information outward, can function as symmetrical structures that determine the initial conditions. If the Big Bang was a white hole, then this equal distribution is a direct result of the explosion. In other words, energy was distributed equally throughout the universe. The internal structure of the white hole may have dictated this homogeneity, much like water spreading in all directions. The cosmic microwave background radiation is another indication of this homogeneity. CMB data shows that the light left over from the birth of the universe is nearly the same temperature at every point. This confirms that the universe had an extraordinarily balanced structure at its beginning. The white hole model explains the source of this order, because the explosion was directed equally outward. This equality from the beginning was reflected in the entire structure. Therefore, the flatness of the universe is not chaos, but the product of a planned eruption. The white hole may be the physical source of this plan. If the initial symmetry was not broken, then the universe expanded while maintaining that symmetry. This perspective allows us to see the structural integrity of the universe as order rather than chance. And this order may be the result of the hidden engineering within the white hole. 47. Could time be an illusion? In our everyday experiences, time feels like a continuous, irreversible line. However, some physical theories suggest that time may be merely a form of perception. In particular, Einstein's theory of relativity has shown that time can change depending on the observer's speed and gravitational pull. This gives rise to the idea that time is not fixed, but variable and even fictional. The white hole theory occupies a radical position in this debate. This is because white holes are defined as structures where time flows backward. If time flows outward and backward within a structure, then time is not just a dimension. It is a variable whose direction can be altered. In this case, the idea that time is not an universal and absolute reality, but a relative structure dependent on physical systems, gains strength. Some philosophers and physicists argue that time is merely the order in which events occur and does not actually exist. According to this view, every moment already is, and we feel as though we are passing through these moments. If the Big Bang was a white hole, then what we call passing could actually be a restructuring. Time simply changed direction at the moment of the explosion, and we called it the beginning. From this perspective, time is not a universal flow, but a change in particles, fields, and consciousness relative to each other. And a white hole is a moment that resets or redirects this change. Perhaps we are not in time. Time flows within us. And the white hole that started that flow is the first narrative initiator event in the universe. 48. Could the Big Bang have been caused by an external influence? Whether the Big Bang was a self-sustaining event or the result of an external influence has long been a subject of debate. According to the classical model, the universe arose spontaneously as a result of random quantum fluctuations. However, some theories question this idea of spontaneity. The possibility that the universe was initiated by something else is brought back into the discussion with the white hole model. If the Big Bang was a white hole, then this event could be the result of a process that took place in another system. Perhaps a black hole formed by the collapse of a star in another universe became the white hole of our universe. In this case, the universe was not born as a result of processes within itself, but rather as a result of the effects of another dimension or universe. In other words, there is an external trigger. The death of another universe is the birth of ours. This perspective could also explain why we live in a universe with such well-tuned physical constants. Because these constants did not arise randomly, they may have been transmitted through a process. A white hole is a system that transmits not only energy, but also order, structure, and rules. This order could be a reformed version of structures that were valid in another universe. In other words, we are the echo of another system. In conclusion, the Big Bang may be the result of an external process that is so conscious and meaningful that we cannot say that the universe started on its own. The white hole model is one of the strongest candidates for physically explaining this process. The universe may not be an explosion, but the breath of another being. Every theory we construct about the birth of the universe is actually pushing a boundary, the boundaries of time, space, mind, and perhaps even reality itself. The white hole theory pushes this boundary one step further because it questions not only where we came from, but also what we are. Perhaps we are the last breath of a star that no longer exists in another universe. Perhaps we are a consciousness, an algorithm, or the outward expression of a thought. But whatever we are, the immense order within the universe whispers that it is more than just a random spark in the void. And perhaps the greatest question remains unanswered. Are we looking at the universe from within, or are we the universe itself? If you enjoyed this mysterious journey, don't forget to like the video, leave a comment, and subscribe to the Liminal Science channel. Your support helps us bring the deep silence of the universe, the magic of the planets, and the boundless imagination of science to more people. Remember, the universe is not just made of stars. It is also made of the lights within the darkness, the silent whispers of space, and the questions of the curious mind. The path to truth sometimes begins not with the glow of a supernova, but with the whisper of a thought. Stay with us and continue to explore the unknown together.